Hello to you all. My name is Dori. To be here. I'm the CTO of Incredible, which is based in Tel Aviv, Israel. That's my first time in Minsk, but I'm giving frequent speaks in various many C++ communities around the world. And today I'm going to present to you a session that is very close to me. This is a session I've created myself. And it speaks about the differences and considerations we need to take when deciding computing architecture to take in our development. So we are going to focus about the differences between multi-process and multi-threaded application. The reason that I'm giving this motivation for assembling this presentation is that usually in the university we are learning about the difference in the technical differences between a thread and a process. But no one teaches us when to choose to write a multi-threaded application or a multi-process application. I'm in the market, in the high-tech market, for more than 20 years. I give a lot of consulting to many companies in Israel on various architecture topics, and especially in Incredible, where we are doing distributed compilation, distributed processing. Companies coming to me and asking me about ways to accelerate their products. And as part of this conversation, I understood that people usually do not consider, and they don't take the time, which kind of parallel architecture is best for their product. Usually when you need to have some multiple tasks, the most common thing the developers and designers are doing is to simply write a thread. 2 threads, 10 threads, and they don't consider whether this is the correct architecture for the product, and especially for the future of their product. I've looked in the web in order to find out whether there are materials about this kind of consideration, and there was none. So I raised the glove, and I decided to prepare this kind of session myself in order to educate the C++ community about they need to think before taking the decision of how to parallel their computation tasks. So first thing, just to give an overview, everything started with, so Moore law has an assumption that the processing time, the clock speed, will double every 2 years. And this was correct. It was held that way for a long time. But starting in 2005, hardware companies started to understand that they are reaching a limit, that doubling the CPU speed every 2 years is something that will not and they needed to have a different strategy to allow us, the developers, to have more compute power. So the way that they decided to tackle it is by adding more processors, more CPU units. Instead of having a single CPU unit, which is better every 2 years, they just added more and more CPU units, and our large customers now have 128 CPUs on a single machine. So this is very good because it allows you now to scale your application and make it much faster. But if in the past you could just buy a better hardware and your application would run much faster because you had a better CPU, multi-process, if you're using a multi-core architecture hardware, your application needs to be developed in a way that will be able to benefit from multi-process architecture. Have many tasks, they need to be non-dependent between one another, and it needs to be scaled, to be able to scale and use more and more cores. So you need to write your application in order to benefit from a multi-process, multi-CPU architecture. So let's start with multi-threaded, and what I'm going to do now is just a very high overview about the pros and cons of multi-threaded versus multi-process. So the common thing about the benefit, the motivation of writing a multi-threaded application, sharing your data. Sharing data between threads is very easy. The only thing you need to do, you have a process. Each process has all the memory, and the threads just use the same memory in the same process space. Just use variables, you can use classes, you can use maps, hash, and you have a lot of third-party libraries that allow you to have classes that are already thread-safe, that make sure that two threads will not write to the same memory at the same time. So this makes it very easy. Another thing is that it's easy to communicate with the parent process. If you have a common variable with the parent process, it's very easy for the threads to communicate with one another and with the parent process. And it's also very beneficial when you have a very large data set that you want the threads to read from, especially when you want the threads to read from. The core application, and I think that's one of the majors, is when one thread crashes, fails, it will fail your entire application. And that's a problem, especially if your threads, if your tasks are, and it will take you time to stabilize your code. This is something you need to take into consideration. It's very complex to debug a multi-threaded application. I don't know how many of you have written a very complex threaded application, but when you have race conditions or some memory overflow, these are very, very complex bugs to solve and to debug. And it usually also requires very developers in order to do that. So you also need to consider your team and whether you have veteran developers in your team. Another thing is that if you have a lot of threads in your application, you will actually lose time in context switching, because your process will always context switch between the threads, and you can lose time instead of gaining performance. And the last thing is that you cannot easily scale. If you have threads and now you want to scale to the public cloud or cluster, use other machines, this is something that's practically impossible in a multi-threaded application, and we will discuss that later on in more detail. We're now going to talk about multi-process. So when I'm speaking about multi-process, I don't mean that I'm speaking about only scenarios that have many processes and that's it. When I'm speaking about multi-process, it can be multiple processes. Each process can have multiple threads. So when I'm speaking about multi-process, I'm speaking about multi-process in scenarios that any process can have a lot of threads as well. One of the main benefits is that when a process fails, fail your entire application. Just this process, this specific process will fail, and that's a large benefit. So for example, in Incredible, in our product, one of the things that we do as an infrastructure that we provide is to execute customer developed. For example, if you have your custom tests, Incredible can take these tests and execute them across machines. So these tests can fail because maybe you didn't write your code well. With Incredible, because it's an application, even if this process fails, we can simply recover. We can recover, we can run it again. And our multi-process architecture is also multi-threaded. It's not only multi-process, every process has multiple threads. To debug, it's more encapsulated. So it's easier to debug a specific process because you can run it separately instead of running a very, very multi-threaded application, which it's much and it's scalable. You can execute in a cluster, you can distribute to the cloud, and also it can consume more memory. If you're writing a multi-threaded application, then your threads can use is the memory that the process has. In a multi-process application, every process has its own memory. If you maybe remember, several years ago, in Chrome browser, one Chrome executable. And the memory that Chrome allocated was very, very high. And it just crawled after a while, and you needed to shut it down and restart it again. Your Chrome now, you will see that you have many Chrome executables. For each tab, you have a Chrome executable, which allows it to consume more memory. So this is very important. Sometimes when you think about the design of your application, you say, I'm just writing, the problem is small, I'm not going to consume a lot of memory, but then in a good scenario, your product catches and everything runs well, and you have more and more customers, and when you're a larger customer, the problem grows. And when the problem grows, you need more memory, you need more processing power, and this is when you need to have both scalability and multi-process can be something that you'd like to consider. You need to consider that before you start developing your product and not when you reach the limits, as was the scenario in Chrome. So what are the cons in multi-process? If you want to share data or communicate between processes, you'll need to do custom development, which means that you'll have probably, you need to develop more, you can have some latency, some more stability issue and bugs. So if you have a lot of synchronization between your processes or your elements, maybe multi-threaded is better for you. Also, there is a way to do to achieve very good performance when you share memory between processes, and this is what we do in our product in Incredibuild. But in order to do that, you need to use shared memory in the local machine between the processes. And this is also, which is viable. You can do that. We are doing it, but it's very complex to develop, especially when you need to synchronize between your processes, and then you need to use some special synchronization mechanisms, such as semaphores or mutexes, on this. This can be very complex to debug and to maintain. So what are the subjects that we need to consider before we develop our application? Which one is better for us, for our requirements? So the list of topics is, first of all, I need to understand whether I need to synchronize data between the threads, between the tasks, whether it's threads or processes. When synchronization, if it's read-only from the same memory, or if I need to write and share data between these tasks, this is something I need to consider. What's the size of my data set? If it's a large data set, if I can divide this data sets, what is the future data set that I can expect in 3 years, in 5 years, when my product will catch and be more mature? How easy it will be to develop the product, and the scaling. We will discuss each of these now. So synchronization and state management is when I need to maintain a state and communicate between the tasks in my application. It's much easier in multi-threaded because I don't need to maintain or use sockets or things like that. I can use hash and maps and things like that inside my application. It's easier to debug this kind of synchronization in a multi-threaded. And as I said, multi-process, it will require custom mechanisms. And third parties you have a lot of third parties to do that in multi-threaded applications. Scalability, so ease of development, yeah. As I said, many libraries for multi-threaded. Multi-process can be developed by less experienced customers, less experienced developers. So you can break your application several processes, and each process is an application. It's much easier to develop. It's much easier for large teams and large applications. So if you consider a very large application, Photoshop, for example, and everything is multi-threaded there, every developer to run the entire application in order to debug a very small piece of code. And everyone will work at the same code. And then if someone will do a check-in in a team of 100 developers, this check-in can break another person's code very easily. Encapsulate a very large application into multiple processes. Everyone will be able to work on a different project, and then it will less affect other developers in the team, and it will be easier for every developer to debug, to commit his code, etc. Okay. So one of the main topics about parallel computing is scalability, and this is especially right when we have a lot of tasks to perform. We have a lot of customers that are doing it. Either if it's financial and gaming and rendering and graphics and simulation and CAD and CAM and compilation and testing, areas in which high throughput is very relevant. And in these cases, if you have an application that you are going to develop that can have a lot of tasks that are to be executed in parallel, you consider many things. One of them is that how many tasks are you going to have? If you have only one or two, maybe you don't need to consider that much. Maybe a multi-threaded will be very easy for you. If you have millions, you need to understand whether these millions of them is going to take just a few milliseconds, or if it's going to take many minutes. What's the initialization time versus the calculation time? How large is the data that each task will require? If it's a large data, all the tasks share. This is a very different scenario than if every task requires just a very small amount of data, for example, in password cracking. So you just need to have a small parameter and you do a lot of calculation. So these are and of course, how much memory will each of my tasks require? So if I will need a lot of memory, then in multi-threaded, if every thread will require a lot of memory, I will reach my limits and my eventually crash. And that's something that a lot of companies and many products are hitting some kind of ceiling. They didn't think that they will need a lot of memory, but then as the product grew, they consumed more and more memory. Some other consideration is the performance. Do I have a real-time system? Do I need to scale? Can I offload? So for example, in scenarios in CAD/CAM simulations, these processes can be so much consuming. So if a developer will run it on his laptop, he won't be able to continue working. So you can offload everything to a different machine and keep the developer or the user's laptop or workstation or other stuff as well. Another thing is, if we're considering scalability, we have today the public cloud, which is something that makes our life very easy in terms of scaling and distributing processing to the. And another thing that you can consider if you have a high throughput task, parallel computing, is to offer your users in the future some kind of business aspect of a SaaS solution. And you may have other questions as well, such as, for example, if my task can run better on a specific hardware. For example, if GPU, there are tasks that can run much faster on a discrete GPU hardware than on a regular laptop. So if I have this kind, for example, rendering or financial derivatives analysis, if I can run it much faster on a discrete hardware, I can take the specific task that has all this calculation, all this rendering, and just write it as a process, and then I can distribute this process to a specific hardware, discrete GPU, and then this specific process will run much faster, and I can separate it from other parts of my application. So as we said, simple scenarios, multi-threaded scenarios, real-time performance, long initialization time when we want to synchronize data between our tasks. If we do a POC, very small POC, so we don't need to consider much. And if we have only very few tasks that just go up and down very, very quickly. Multiprocess is very good when when we can encapsulate our processes, our models, and when we have large that are developing a very large application. When we have a lot of processes and we would like to distribute them and parallel them to the cloud or to the cluster in the future, and when we know that we have tasks that are prone to errors. So there are scenarios in which, for example, you have very complex financial algorithms and you know that they can fail. It will take you much time to stabilize your system with the users, and you want to be able to recover. So this is also a multi-process scenario. So one of the main challenges, as I said, is when you have a lot of tasks, when you have a lot of compute, high throughput, and that's a real challenge. And in order to just take a real-life scenario of this, I'm going to compare between two tools. I'm not sure if everyone is familiar with these tools. These are very popular tools, Maven and Make. Maven is, they are both build systems, so we can compare between them. Maven build system, and Make is a C++, usually used for C++ code builds. They are both very popular. They have a lot of tasks. Each of them compile a lot of units. These tasks, so every task has everything that it needs, usually a file as an input and a file as an output. They have minimal communication between these files. They have small data sets, and they can scale. So we are going to take these two tools that these two tools started, I believe, more than 10 years ago, and we are going to see which strategy each of them took and where did it lead it. Okay, and we can learn from it in our scenarios as well. Maven is a multi-threaded. They decided to go for multi-threaded, and Make is a multi-process. So in fact, Maven was a single-threaded build tool, and multi-threaded was a few years ago. But still now it's multi-threaded. So essentially it can run on all your cores, but it can only run on your local machine. So as you can see here, there are customers complaining about very large projects in Java, and they can only use their local cores. So in the past it was okay because you had smaller projects, smaller third parties, but in today's world of a lot of open source and use of, when you compile your code, you're actually compiling a lot of other stuff as well. So the code builds became very, very large. And compiling a very large Java application on a 16-core workstation can take a long time, even if it compiles very quickly opposed to C++. So now that Maven is multi-threaded, it's very complex for the Maven developers to make it it's multi-threaded, it's very complex for them to make it multi-process. Sometimes in Maven takes long time, and so that's a limitation. This is how it looked like. This is what I'm showing here is a snapshot from Incredible Monitor, just to show you a demo of how things are looking when you're compiling on various scenarios. So each line here is a core. So this would be how it would be shown if you had only a single core. You see every task being compiled, okay? But now that it's multi-threaded, Maven, so you can have multiple cores. You can see here 8 cores, and you can see all these tasks being executed on 8 cores. But that's the limit. On my 8 cores, and I can't compile on more than 8 cores my Java code build. As opposed to Make. Make is a multi-process. So the memory usage is much better if I have very large, but in compilation you don't memory occupation, so it's fine. But one of the things that the multi-process architecture that Make took help them is that a lot of third-party tools could take benefit of execution in order to build add-ons on top of Make. Because In a multi-process application, I can see which process is being executed. So I can see the process name, I can see the parameters this process is taking, and I can see rules that go on top of that. In Maven, I can't see inside. I can't see which threads are being executed. I don't have visibility into the tasks. So in Maven, in order to write a plugin for Maven, I need to go inside code, and whatever Maven exposes to me, I can write a plugin for it. But in Make, I can simply take the tasks, the processes that are being spawned, and do a lot of things for that. So for example, you have Ccache. It's a caching solution for Make. Cache the results of your compilation, because it sees which task you are doing, which files you are compiling, so it can cache these files. You can have a distributed solution in order to accelerate your compilation time, such as DCC and Ice Cream, and commercial tools such as Incredible, because we can see the processes being executed, so we can do things with them. For example, if we've seen this, and this is an example of Qt library being compiled on an 8-core machine. So if you can take a look here, you can see that all these tasks are being executed in a sequential manner, one after another, and they are not parallel. This is because that's the way Qt wrote the. But for example, in Incredible and other tools as well, when we know which processes is being executed, we can do an out-of-order execution. We can change the way these processes are executed, and we can run them in parallel, although the make script was running them in a sequential manner. So this is something, so if you have your own products written in a multi-process, other products or other things can extend in open source. Other products can extend them by looking at your multi-process execution and do some things on top of that. Another thing is the ability to distribute. So within this source or Incredible, you can take all these compilation tasks, and instead of running them on 8 cores, you can run them on hundreds of cores. This is a Qt running on 200 cores with Incredible. So you can see here the scroll bar, and you can see the dot to scroll. So on my laptop machine, I can use 200 cores, and you can do that in a commercial product, or you can do that for free in an open source such as this CC. And that's because the application is multi-process, and other open source can take advantage of it. So let's take a look at other real-time scenarios of applications and which kind of processing, parallel computing architecture it's relevant to take. So multi-threaded, and that's just a direction. It's not always like that, but that's the common scenario. Okay, so if you have large in-memory data sets, for example in CAD, weather forecasting, genetic algorithms, when many tasks need to read a very large set of memory, and we are focusing now on scalability. And they need to communicate a lot of in them. If you are, for example, in AI or genetic algorithms, you have some kind of task that need to communicate and calculate scales and things like that. So you usually write it in multi-threaded. You will not take a 4 or 5 giga memory and distribute it to another machine. You can do that in multi-process on a single laptop in a in shared memory, but this is not a major benefit. It is better in this scenario. Another scenario is when you have real-time performance is needed. If we are speaking about financial transaction, defense systems, where performance, you need to have it very, very quick. So you want to have multi-threaded, usually, because when one thread waits for I/O, the other thread can do some calculations, but you need it very fast. You don't know you have this initialization time of a process and the communication time, the latency of communication time that it takes. So multi-threaded for real-time is usually used. When we have a database application, Most of the calculation is in the database side. If we're speaking about stored procedure, all cubes, triggers, stuff like this, there's no reason why not using multi-threading, unless the results that you are getting for the database are very large and you want to keep them on each task, and then you are reaching the memory boundary that we spoke about before. So these are usually CRM, ERP, SAP, for example, this kind of application. Another one is when you have sequential processing. So you want to have a lot of threads or a lot of tasks, but each one relies on the other. For example, cutting applications, manufacturing line, or dependent calculation. This is usually multi-threaded as well. So multiprocessing, usually when you have, but you can divide this data set into smaller data sets. For example, rendering. When I have a movie, when I want to render a movie, and it's a 1.5 hour movie, it can take a day to render a movie of 1.5 hour. But I can break it from, instead of running a full 1.5 hour, I can run 91 minutes frames rendering. So this is a large data set that I can break into multiple data sets. So these are simulation financial derivatives, for example, when you want to calculate some kind of financial algorithms per paper, per stock, rendering, and other scenarios. In fact, ANSYS and PSCAD are they are doing simulations, and they wrote their application in a multi-process manner at the beginning, when it was very, very young. All this industry was very young. And now they can scale very, very efficiently, and ANSYS have a solution to scale the computation to the cloud. Usually to run a very, very large simulation of ANSYS, it can take a week. And with the cloud, and they offer it as a SaaS service, it can take hours. And large companies are just in order to run their simulation faster. ANSYS has competitors that didn't write their application in a multi-process manner, so they are stuck on the local machine. So their customer now need to purchase very expensive 20 core hardware just to run it in a better performance, but they are still having some kind of limit. And they cannot make it better. The performance is just limited to the amount of hardware they can use. Relevant, and now ANSYS is leading the market in this kind of simulations because they can run it much faster. And for the other companies, they just need to change the entire product in order to do it multi-process, now that these products are very mature. So that's very important. In scenarios when you have a lot of calculation with small units. So for example, we're speaking about compilation and testing and code analysis and rendering and asset builds. And in the gaming industry, you have shading and you have rendering and you have making and a lot of other stuff. When you have math calculations, so multiprocess is extremely good there because you can scale. You can scale your processing. And just looking at the, all the papers that you have here. So Incredible as an infrastructure to distribute tasks to a remote machine. As we are a generic infrastructure, there are a lot of things here that are written in multiprocess. I don't know if you see the red dot. CLion is a C++ compilation tool that is written in multiprocess. TeamCity, which is the continuous integration tool of JetBrains, is also a multiprocess application that all the QA automation, for example, Google Test and MS Test and VS Test and a lot of others are multiprocess, and Incredible accelerates these as well. Also, some other scenarios, Viva 64, PVS Studio, is something that is written in multiprocess fashion, so Incredible can accelerate this as well. So essentially, if you have multiprocess, you have visibility and other things in the market visibility in order to provide some advantages to it. Other multi-process scenarios, GPU. So if we're speaking about CUDA, OpenCL, rendering, password, finance, it's very popular today. And there is a very, very big difference when running GPU in a laptop graphical unit card or in a discrete graphical card. So this is also when you want to be able to offload this task maybe to a better processing unit. Streaming is also a multi-process classic scenario. For example, if we're speaking about Netflix or NVIDIA Shield or workstation systems, essentially everything that has a daemon that serves a user. So if you have more users, you simply have more daemons. Having these daemons as threads, you will reach a limit. You will need to understand what's your memory limit and what's your network limit, etc. But if you have multi-process, for every user, you'll just run another daemon, another process for every user. It's very easy. And with the public cloud, it makes it even easier. The business aspect. As I said, you can price for this. So if you have an application and you need to design application, you need to consider if this application in the future scale, you will need to have larger problems. This is something you can take extra money for. That's business, and that's something usually your CEO or whatever if it's a small company, they will tell you, listen, we need to do that. Your role as the technical expert, if you're the dev leader, to tell them, listen, we can also have a SaaS service in the future. We can charge for it extra money. That can be part of our business operation. To have either the public cloud or a SaaS solution or an offloading solution. That's something that needs to come from the technical people because the business guys are not familiar with this kind of technologies and concepts usually. So to summarize, there are a lot of considerations. Just take the time to think about it. It can highly affect your application. As I told you, there are products which in the beginning were really process way, and that's what gave them the lead, the hedge over other products. As I mentioned, ANSYS, for example. Now ANSYS is the market leader just because of this, just because they have the best performance for simulation. And to have the best performance, better time to market for the users, better ability to sell and price it, if we're speaking about SaaS, and better user experience. So that's highly relevant. So just take the time to consider what both in architecture level and also in the development technical level. Consider your teams. Do I have expert developers? Can I encapsulate? If you can encapsulate, so make it a process. Why burden the entire application with this specific process? With this as a thread. So you need to consider what it is that you have, whether you can encapsulate it, what's the synchronization in these elements. If you don't have a lot of synchronization, again, processes are very good. What's the level of your developers? What's the complexity of your code? If you need special hardware, or if the special hardware can make your run faster. Some business aspects of this consideration, whether you can benefit from it or not, who is your user, how complex is your application, all these things, please consider in advance and don't try to write another thread, okay? Just give it, even if you give it 2 hours or 3 hours of thought, this can really affect the future of your product. So that's it more or less. Just about Incredible, Incredible is a generic infrastructure that allows you to distribute processes across machines in a seamless manner. We're having some very, very nice virtualization mechanisms. Another topic that I'm giving as well, how to virtualize stuff. And you can accelerate compilation, test, and any other multi-process execution with it as an infrastructure. But again, the main purpose of this was your product and the products you're writing. So just make sure you're giving it a good thought. Yeah, I'm open for questions. Thank you.
Hello.
Hello.
Thank you for your presentation. It was really interesting.
Thank you.
But I have a question, not about your presentation, but about Encrypt. Will it ever support Mac or iOS builds?
You're not the first one asking about it.
I know, but still.
Not in the near future, but this is something we are considering. We have some design partners that are asking for it, such as Adobe and other very large companies that have a lot of Mac and iOS. And this is something we are considering, very considering. Maybe next year we'll have some news, but for now.
Okay, thank you.
You're welcome.
Can you give us a little bit of technical details about how Incredibuild split building of Android NDK tasks on several machines?
Okay. That wasn't the main focus of the presentation, but I will give just a few words about how Incredibuild does that. So essentially, as I said, when you have multi-process, other applications such as Incredibuild can have visibility. The way that we are doing that is we inject code into the master process. So just for other people to understand what we are talking about. Incredibuild is a tool that allows you to take any multi-process and just take, so for example, if you have make and you have a lot of GCC tasks, you can just run your make command with Incredibuild. Incredibuild will take all these GCC tasks and run them on all machines in your network. So instead of just using 8 cores on your laptop, you can use 800 cores to compile in parallel, and then you will compile in much faster. So how do we do that essentially is that when you execute your command, for example, make Android with Incredibuild, we inject code, our DLL, into this main process. So we inject Incredibuild DLL to this make process. And then we intercept what make is doing with the operating system. So for every create process that make is doing with Windows, for example, we intercept this call, and Incredibuild gets this call before this call reaches the operating system. So we want the process, so if make execute create process GCC, we don't want GCC to run on the local machine. We want to run it elsewhere on an Incredibuild agent we have installed on another machine. So we don't let this create process call operating system, and instead we give a fake handle to the parent process. And then we take this GCC command. This is a process, so we have all the command, right, as I said, and we pass it to an Incredibuild agent on another machine, ask this agent to run it there. This agent will take this command, and it will run this command there. We pass also the executable itself. And now when this agent on a remote machine, this remote machine doesn't have anything. It doesn't have make, it doesn't have the input files. It's a plain new machine from the store, for example. So we run the process there, this GCC, and again we inject an Incredibuild DLL to this machine, and we intercept all the calls that this GCC task, this remote machine. So when this GCC task will open a file, we will not open the file on the location. We will instead wait, we will take this call, we will bring this file to our location and cache it on the remote machine, break the call. So this is a complete virtualization. So Incredibuild is not only an infrastructure for parallelization, it's also a virtualization. And maybe next year I will give a talk about how to do virtualization in C++.
Any more questions?
Okay, yeah.
Thank you for speaking.
Thank you.
Please, could you please clarify? You said that multi-process systems can have better memory management. It's completely true when we're speaking about 32-bit systems because we have limited address space and we can allocate more than 2 gigabytes of memory. But what about 64 architecture? We can allocate, we have huge address space, I can allocate any amount of memory that we wish. So what do we mean when saying better memory management?
So yeah, you're right. 32-bit is the common scenario that I'm referring to. But also, when you allocate a very, very large memory for a single process, even if 64-bit, you can reach some performance in terms of memory, even in a 64-bit application. So it is also a good practice if you require very, very lot of memory, and your process, instead of allocating 30 in a single process, to break it into multiple processes will give you better performance in terms of access to the memory and the way that the operating system handles its memory. But as you said, most of it is usually systems. But when we're considering an application, and I can tell you as a CTO of a product that has a lot of customers, 32-bit is still there. You have a lot of machines, you have a lot of legacy machines which are still 32-bit, and you need to know. But that's a good question. Thank you.
Thank you, Dori.
Thank you all. It was a pleasure to be here.